In the year 1919, a virtually unknown German mathematician named Theodor Kaluza suggested a very bold and, in some ways, very bizarre idea. He proposed that our universe might actually have more than the three dimensions that we are all aware of. That is, in addition to left, right, back, forth, and up, down, Kaluza proposed that there might be additional dimensions of space that, for some reason, we don't yet see. Now, when someone makes a bold and bizarre idea, sometimes that's all it is. Bold, bizarre, but it has nothing to do with the world around us. This particular idea, however, although we don't yet know whether it's right or wrong, and at the end I'll discuss experiments which in the next few years may tell us whether it's right or wrong, this idea has had a major impact on physics in the last century and continues to inform a lot of cutting-edge research. So I'd like to tell you something about the story of these extra dimensions. So where do we go? To begin, we need a bit of backstory. Go to 1907. This is a year when Einstein is basking in the glow of having discovered the special theory of relativity and decides to take on a new project to try to understand fully the grand pervasive force of gravity. And in that moment, there were many people around who thought that that project had already been resolved. Newton had given the world a theory of gravity in the late 1600s that works well, describes the motion of planets, the motion of the moon, and so forth, the motion of apocryphal apples falling from trees, hitting people in the head. All of that could be described using Newton's work, but Einstein realized that Newton had left something out of the story because even Newton had written that although he understood how to calculate the effect of gravity, he had been unable to figure out how it really works. How is it that the sun, 93 million miles away, somehow it affects the motion of the Earth? How does the sun reach out across empty, inert space and exert influence? And that is a task to which Einstein set himself, to figure out how gravity works. And let me show you what it is that he found. So Einstein found that the medium that transmits gravity is space itself. The idea goes like this. Imagine space as a substrate of all there is. Einstein said space is nice and flat if there's no matter present. But if there is matter in the environment, such as the sun, it causes the fabric of space to warp, to curve, and that communicates the force of gravity. Even the Earth warps space around it. Now look at the moon. The moon is kept in orbit, according to these ideas, because it rolls along a valley in the curved environment that the sun and the moon and the Earth can all create by virtue of their presence. If we go to a full-frame view of this, the Earth itself is kept in orbit because it rolls along a valley in the environment that's curved because of the sun's presence. That is this new idea about how gravity actually works. Now, this idea was tested in 1919 through astronomical observations. It really works. It describes the data. And this gained Einstein prominence around the world. And that is what got Kaluza thinking. He, like Einstein, was in search of what we call a unified theory. That's one theory that might be able to describe all of nature's forces from one set of ideas, one set of principles, one master equation, if you will. So Kaluza said to himself, Einstein has been able to describe gravity in terms of warps and curves in space, in fact space and time to be more precise. Maybe I can play the same game with the other known force, which was at that time known as the electromagnetic force. We know of others today, but at that time that was the only other one people were thinking about. You know, the force responsible for electricity and magnetic attraction and so forth. So Kaluza says, maybe I can play the same game and describe electromagnetic force in terms of warps and curves. That raised a question. Warps and curves in what? Einstein had already used up space and time, warps and curves, to describe gravity. There didn't seem to be anything else to warp or curve. So Kaluza said, well, maybe there are more dimensions of space. He said, if I want to describe one more force, maybe I need one more dimension. So he imagined that the world had 4 dimensions of space, not 3. And imagined that electromagnetism was warps and curves in that 4th dimension. Now here's the thing. When he wrote down the equations describing warps and curves in a universe with 4 space dimensions, not 3, He found the old equations that Einstein had already derived in 3 dimensions. Those were for gravity. But he found one more equation because of the one more dimension. And when he looked at that equation, it was none other than the equation that scientists had long known to describe the electromagnetic force. Amazing. It just popped out. He was so excited by this realization that he ran around his house screaming victory, that he had found the unified theory. Now, clearly, Kaluza was a man who took theory very seriously. In fact, there's a story that when he wanted to learn how to swim, he read a book, a treatise on swimming, then dove into the ocean. This is a man who would risk his life on theory. Now, but for those of us who are a little bit more practically minded, 2 questions immediately arise from his observation. Number 1, if there are more dimensions of space, where are they? We don't seem to see them. And number 2, does this theory really work in detail when you try to apply it to the world around us? Now, the first question was answered in 1926 by a fellow named Oscar Klein. He suggested that dimensions might come in 2 varieties. There might be big, easy-to-see dimensions, but there might also be tiny, curled-up dimensions, curled up so small, even though they're all around us, that we don't see them. Let me show you that one visually. So imagine you're looking at something like a cable supporting a traffic light. It's in Manhattan, near Central Park. It's kind of irrelevant. But the cable looks one-dimensional from a distant viewpoint. But you and I all know that it does have some thickness. It's very hard to see it, though, from far away. But if we zoom in and take the perspective of, say, a little ant walking around, little ants are so small that they can access all of the dimensions. The long dimension, but also this clockwise, counterclockwise direction. And I hope you appreciate this. It took so long to get these ants to do this. But this illustrates the fact that dimensions can be of 2 sorts, big and small, and the idea is that maybe the big dimensions around us are the ones that we can easily see, but there might be additional dimensions curled up sort of like the circular part of that cable, so small that they have so far remained invisible. Let me show you what that would look like. So if we take a look, say, at space itself, I can only show, of course, 2 dimensions on a screen. Some of you guys will fix that one day. But anything that's not flat in the screen as a new dimension goes smaller, 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 and way down in the microscopic depths of space itself. This is the idea. You could have additional curled up dimensions. Here is a little shape of a circle, so small that we don't see them. But if you were a little ultra microscopic ant walking around, you could walk in the big dimensions that we all know about. That's like the grid part. But you could also access the tiny curled up dimension that's so small that we can't see it with the naked eye or even with any of our most refined equipment, but deeply tucked into the fabric of space itself, the idea is there could be more dimensions, as we see there. Now, that's an explanation about how the universe could have more dimensions than the ones that we see, but what about the second question that I asked? Does the theory actually work when you try to apply it to the real world? Well, it turns out that Einstein and Kaluza and many others worked on trying to refine this framework and apply it to the physics of the universe as was understood at the time, and in detail it didn't work. In detail, for instance, they couldn't get the mass of the electron to work out correctly in this theory. So many people worked on it, but by the 40s, certainly by the 50s, this strange but very compelling idea of how to unify the laws of physics had gone away. Until something wonderful happened in our age. In our era, a new approach to unify the laws of physics is being pursued by physicists such as myself, many others around the world. It's called superstring theory, as you were indicating. And the wonderful thing is that superstring theory has nothing to do at first sight with this idea of extra dimensions. But when we study superstring theory, we find that it resurrects the idea in a sparkling new form. So let me just tell you how that goes. Superstring theory, what is it? Well, it's a theory that tries to answer the question, what are the basic, fundamental, indivisible, uncuttable constituents making up everything in the world around us? The idea is like this. So imagine we look at